when you need to perform a big task or some complex operation, you usually break it up into simpler steps. So, for example, if you want to build a house, you usually break it up into simple steps of first you're going to dig a hole. Once you have the hole dug, then you're going to pour footings. Once you have footings, you're going to form up, say, the basement walls. And then once you have those forms, you're going to pour concrete. So it's a step-by-step process for building a house. We can think of functions, too, as being built out of simple steps that create the complex function. For example, this function h of x, actually we could think about it as two simple steps. So first, we have a function where we're going to take a number, cube it, and subtract 5. Then the next step will be to take the square root of that. So we have written here h as a composition. We start with an x, we plug it into g to get x cubed minus 5, and then we plug that into f in order to take the square root of that. So that creates that composition. Now, we're calling this function's name h, but when you compose two functions, sometimes you say, well, since f is around g, right? So a good name for that would be f compose g. We use this little open circle to indicate that f is around g, or f compose g would be a good name for composing those two functions would be f compose g. So notice as far as derivatives are concerned, I've broken it down into two simple steps. I know how to take the derivative of this function because it's by the difference rule I can just take the derivative of this power minus the derivative of a constant, which is 0. This is also a power. This is x to the 1/2, so f is a function that I can differentiate. So our first step is to recognize a function as steps, right, where hopefully each step is something that we know how to take the derivative of. In a second, we'll see how to use the derivatives of the individual steps in order to get the derivative, or the instantaneous rate of change, in other words, of the entire process. Let's just practice a few more of these recognizing compositions. Here's a function. We could think of the first step maybe as calculating e to the x plus e to the minus x, and the second step is just raising that to a power. So whatever we've got, and we'd raise it to that power. That way we're starting with x, we plug it into g in order to get e to the x plus e to the minus x, and once we've got that, we plug it into f in order to raise that whole thing to the 5th power. So we've taken this function, broke it down into simpler steps. Now that's not the only way you could do it. There might be multiple ways to do it. One thing might be maybe here's an alternate version. Maybe we'll have this function k, and k is just going to calculate e to the x, and then h is going to give us maybe oh, I already have used h. How about I call that L then? The function L is going to give us x plus 1 over x, and then maybe we'll have another function m, and m's job is going to be to raise everything to the 5th power. So if I take m of L of k of x, I have now here a 3-step chain, right? First what happens is the number goes into k and out comes e to the x. Now what L does is it takes a number and adds its reciprocal. So if you give it e to the x, it's going to take e to the x and add the reciprocal of e to the x. But 1 over e to the x is the same thing as e to the negative x. So then we'll have that go into m. Now what m does is whatever you give it, it raises it to the 5th power. So, oops, I need to plug all that into m. So that's going to go into m. M will take your e to the x plus e to the minus x to the 5th. So there can be more than one way to break down a function as a composition of simpler functions. What we're looking for is just the way to break it down so that it is a composition of functions that we know how to take the derivative of. Either one of these ways would work. So we have either h is f compose g of x, or with this other system, we're taking m around L around k, right, of x. Either one, whatever works for you. Okay, so let's work some more here. I see an easy way to do this one. Maybe let the inside function be x plus 3x cubed, and the outside function can be sine x. So broke it down into composition of two similar functions, right? With this choice for f and g, h is actually the same thing as f compose g of x, or f of g of x. This one could do this. So you think cosine squared of x, that's actually the notation. This 2 on the name of cosine indicates the function where you find the cosine and then you square it. So we can see one way to do this would be to say the inside function is cosine of x and the outside function is x squared. We've decomposed this composition. We just do a couple more. Say, well, our first step is to multiply the input times 3 and know how to obtain the derivative of that. And then the second step would be to take whatever you're given and make it the exponent on e. And then f of g of x, we start with an x. G of x makes 3 times whatever you started with, and then f is the function that whatever you give it, it makes it the exponent on e, so this would be e to the 3x. So yeah, we've written h now as a composition of two functions. It's f composed g of x, or f of g of x, like that. All right, let's see. This one's pretty similar, isn't it? So the g of x, the inside function would be the tangent of x, and the outside function would be e to the x in that case. All right, so our next step is going to be, once we've recognized some composition, then what we're going to do is we're going to figure out how do you take the derivative of that composition.